Okay, good morning. So let's continue studying water waves and through potential theory. And let me give you the dimensionless equations, and one reference I mentioned just very quickly is Witham's book, okay? Linear, nonlinear water waves. Waves, not water waves. Linear and nonlinear waves. Great book in waves. And here's how the system we have, which is an excellent, as I mentioned, playground for many mathematical ideas, techniques. So I have to write this again to make sense for today's class. I make this explicit. In our free boundary problem. Put it like this. I'm already doing the flat bottom case. Okay, let's see what else I have to give. Yes, initial conditions. So I put it like this, at free surface this is 1, so this is wrong, right? I forgot I had already dimensionalized. Minus 1. Okay, we have a no, look. So I make a mistake, which is a good mistake, and I'll tell you why. Because since this is 1 plus alpha eta, this means here it's 0, and here's 1 plus alpha eta, which doesn't really matter. Depending on the convenience, we put our reference on the bottom or on the top. So here it's y equal to 0. Okay? So this is a good mistake because it forces me to explain, right? And this does not really matter. It's to our advantage where we put this. What else I want to say? Okay, just for you don't have to memorize this, right? It was the first time. So alpha is nonlinearity. Beta is this parameter, which today you will see, I hope so, what dispersion means. Okay? And this is our problem, right? This is a very, as you will see, non-trivial problem, right? And the analysis actually of this problem in 3D, proving like existence while opposing, these are very recent results in analysis, right? This is a complicated problem, but many things are already understood for some time. Just some of the rigor in function space was not fully developed. There's still questions, right, of interest. And so we did then, let me see, I can put here, so we can have like the review from last class, because this will be important for today. So using a power series expansion about the bottom, we found this. Okay, which is a formal representation of a Laplace equation. So this basically satisfies Laplace plus Neumann formally, right? So I'm calling this not quite, it's a scaled Laplace, right? Laplace equation, and this guy. So we already took care of this. And then we substitute this in free surface conditions. Okay, and this is what we did last class. And we got the following system. We got substitute, so let me put this. Then A, substitute in free surface conditions, B, truncate up to, let me put it in asymptotic notation, order alpha, order beta, okay, which means weakly nonlinear, weakly dispersive, and C, we found, let me call it, because we have, as you will see today, we have infinitely many Boolean-esque type systems. So you understand what I mean. So I'm going to write, we found B, a Boolean-esque type system in the form eta t okay, and where? I have to remind you, U is depth averaged. Okay, the details you have on the notes and you have in the last class, right? On YouTube you can see. So this is the summary of what we did, okay? So this is our first exercise in, right, reduced modeling, right? I may call this, right, in the jargon I like, this is a reduced model because it comes from a parent system of PDEs, right? This is a PDEs and applications course. So from the applications it's water waves, and from now the purely PDEs point of view, right? The story is like this. I have this complicated system of PDEs. I want to identify a regime where I can simplify this guy in a systematic, which I call like educated way. Educated means educated in the partial differential equations, right? Sense that I know that's tricky to throw some terms off or not. I have to be careful. So that's the educated way. So our first attempt to do that was the regime alpha small beta small, which means this. Weakly nonlinear, weakly dispersive, because it's the first correction in these terms of the expansion in the equations. Right? That's what means weakly nonlinear. I always tell this story in the courses. I maybe even have said this here. I once almost offended somebody here at IMPA saying, oh, you work with weakly nonlinear PDEs? And the person said, why weakly? Like if it was something that would diminish, right? Make it sound easier. No, it's not easier. It's just, it's the first term in nonlinearity correction, right? There's no bad sense this. And this is one way, okay, this is one way of doing I'm going to using this term, a harmonic extension of information, namely, taking this guy, which was a harmonic function, and bringing it from its boundary information into the interior using some technology. For example, this approximation. We're going to see later on how to do things in a more elegant way than this, but this is very useful and it's very nice. I like it very much. There's no, right? So once we do this, we now get this system, which is not yet, this is the first thing I'm going to do today, which is new. This is not yet the system Boussinesq found. Therefore, I'm calling it a Boussinesq type system. And as you will see, there's infinitely many of these guys. I can now play with this guy according to some simple rules of asymptotics that probably will give you a short, some short problems that I will suggest today for you to do, okay? And maybe then and formalize it for you to hand. So this is, here it is. Let me highlight our weakly nonlinear, weakly dispersive approximation. And this is a Boussinesq system. And because of this term, we will learn this term here is actually our dispersive term in the sense of Fourier analysis. We will see this. Okay. So I'm going to show it to you. Now let's get, let me call this equation here maybe, okay, let me call this equation 1. From 1, let's obtain a dimensionless version of the original Boussinesq system. So let me first get the dimensionless one, and then I'll show you which is the original one, and you'll see why. Okay? So the trick is the following. It's a trick that appears all the time. So note this. Note, so let me say it. Note that from the first equation here, okay, note that eta t, see if you agree with this. Eta t is equal to minus u of x plus order alpha. This is something we're going to be doing many times now in this game we're playing, this sort of asymptotic game we're playing. It's from here, look. Remember that here in the exact sort of equations from the series point of view, I had here in previous lecture a big O of alpha squared, alpha beta, beta squared, which means higher order terms that I threw away. So I can play with terms, and every time something becomes again alpha squared, alpha beta, whatever, it's a term I can throw away because it's part of that same sort of garbage, that same truncation that I ignored because I'm admitting that it is small, right? If I have regularity and so on. So here, what do I want to do? I can play a game of exchanging derivatives, saying, oh, instead of a spatial derivative in my PD, I want a time derivative. Instead of a time derivative, I want a spatial derivative. So what we're going to do is that this dispersive term here, as you will see, because I'll write it soon, in Boussinesq equations, it was a different term. Okay? So I can exchange, look at this. This is a UX derivative. I can exchange this for a time derivative because it's going to make it look like the Boussinesq equation, which I'm about to show you, using the first equation, which is this. This is the first equation written in a short form, which is u of x, eta of t is equal to u of x plus an order alpha. If I plug this into here, right, I can just substitute this u of x by minus eta of t, because this correction term here, right, is going to get multiplied by beta, and it's going to go into the garbage. If I were to write it as before with the truncation terms, the garbage, what I say informally, colloquially, informally, garbage is the terms that I will neglect because the hypothesis is that they are small terms. And they'll stay small because my function is smooth and these derivatives will not give me trouble or anything, right? Sometimes it's difficult to really check that rigorously, but the hypothesis makes sense as you see the solutions and you compare the systems, you can do that sometimes numerically and so on. Okay, so therefore, so note that and substituting in the second equation, we have the original Boussinesq system, which is like this, dimensionless, right? So the first equation is the same, and the second equation looks like this. Okay, so here is the original. Now, compare with the original Boussinesq system, which is like this. This is from, actually now I have the date, which I always forget, from 1872, and where H is this. Okay, so you see that this system is basically the same, right? This is in dimensional form, right? And what Boussinesq did in 1872 is that he realized that he could get, right, as I mentioned, a depth average velocity, because the velocity didn't change with his physical intuition. The velocity it was shallow with respect to the wavelength. The velocity did not change much over the depth, so the average is representative of something that doesn't change much. The vertical speed was very small because the wave is long too. So if a long wave passes by, it's like the free surface rises kind of slowly and then goes down. So using these hypotheses, he was able to deduce this system, okay? And you can see that this is a dimensional version, more or less, of this. Look, the nonlinear term is the same. The dispersion term is the same. This part here is the same as above, right? So Boussinesq did in some sort of ad hoc fashion, right? Throwing out terms using his great intuition. And we deduced this in a systematic way, which is very good because then we learn in a very good way which are the relevant terms, how they come in, and so on, including for numerics. It's always very good to also use dimensional form, and then you can play with the parameters to increase the nonlinearity, to decrease it, and to see, you know, for example, if I take this guy away, this looks, if you write to the right and left modes, this looks almost like a Burger's equation going one way and a Burger's equation going the other way. Look, the nonlinearity looks at the nonlinearity of Burger's equation. You can get shocks. One thing that in the analysis community, there's a lot of study these days, and I'll talk this maybe next class a little bit, right? Just so you understand is that if you add this term here and this term is much smaller than the nonlinearity, so suppose this is order 1, the alpha is 1, and this is small, you get what's called a dispersive shock, right? Instead, if I put a heat term here, I get a viscous shock. You don't have to understand what I'm talking about right now. But this is when we get then diffusion to come in, terms like the heat equation. So it's something that's very complicated. The viscous shock is slightly simpler than the dispersive shock. I'll mention this to you, and it's not in all detail, but in a way you will understand in the near future. Can't quite say exactly when, but in the near future. Okay? So this is the Boussinesq equation. This is the Boussinesq equation in terms of the dimensionless one. But look, this is a Boussinesq type 1, you know, where the dispersion term is different. Then you can ask me a proper question is, okay, you did in a sort of artificial way, yes, changed this term into that term because it looked like the Boussinesq term, original Boussinesq term, right? And I can still do, as you will see, play more games and still keep on changing these guys under the same physical hypothesis, which is small amplitude over depth, small depth over wavelength. So it's the same physical hypothesis, same asymptotic regime, but I can cook up many different equations. You will see this. And then you can ask, okay, what is the impact of cooking up these many different equations? If we linearize the equations, the answer is quite simple, using Fourier analysis. If you ask that question in the nonlinear regime, then you have to use functional analysis, and the question is not that simple. And particularly to show also the similarities or the differences of the solutions of these equations, namely of the reduced model with respect to the full mother equations. To show this in a functional analytic rigorous way is not an easy question, okay? Gets even more complicated when you go to, say, dispersive shocks, or you want to see traveling waves, or you want to see stability of these. Anyway, there's many questions that are very difficult and are not going to be seen in this course. Okay, so as I mentioned last time, quickly at the end, so if I do the beta equal to 0 regime, which is dispersionless, right? No dispersion. Implies we get a hyperbolic system, which you already know what it is. And let's do the one for, okay, the one I have in the notes is for the original Boussinesq dimensional system. That is with dimensions. Okay, and here it is in conservation form. You know what I'm talking about, right? Conservation form. Are the flux functions. Okay, I have it in the notes, but I'm not going to write here. The dispersion less case in the dimensionless case, which is just make this guy equal to 0, right? You can also write this in conservation form. Just put this x derivative outside, just like we put here. Very easy. Here it's already outside. And if you want to see the characteristics of this system, for example, what do you do? Let me take a sip of water. This is something you should react in 2 seconds. Of course, it's the first time I'm throwing this sort of ball at you, right? Now I have to return the ball to me, poop, quick, fast move. But what are the characteristics here? In other words, what are the speeds here related to the characteristics, the eigenvalues? So if I talk about characteristics, immediate reaction for a system is eigenvalues, right? And then immediate reaction is, okay, I would not be able to say it so quickly off the top of my head, but I can say what to do. What to do is write this in matrix form, in non-conservative form, and then you look at the eigenvalues of the matrix. Okay? Which is basically write this like this. Right? We did this before. You look at this matrix. This matrix is, in one sense, is nonlinear in the sense that it will depend on the solutions. In the linear case, it does not depend on the solutions, right? And therefore, you get the eigenvalues, and you see that this system is actually strictly hyperbolic. What does it mean that it's strictly hyperbolic? The eigenvalues are real and distinct, which guarantees that the matrix is diagonalizable, right? Has 2 independent linear eigenvectors. Okay. And okay, let me, it's so simple. Let me still use this blackboard, right? And be economic for the blackboard so that the camera stays at the same place. Now, if I do this regime, we get okay, so this is the linear hyperbolic with characteristics plus or minus 1. Okay, so plus or minus 1. Speed, because it's normalized, so the speed is plus or minus 1. And moreover, this is equivalent to the D'Alembert type wave equation that we learned as an undergraduate. Why? Because I can, for example, eliminate u from the problem by differentiating this with respect to x, differentiating this with respect to t, differentiating this with respect to x, subtracting, I kill the u, and I get this. Right? So look at the story. So maybe now the camera has to follow me. Look at the story. This complicated problem, which I call the parent equations of many equations, I can sort of start simplifying it, making a reduced model. And if I simplify the regime, right, and make it non-linear and not dispersive, I get this system, or even I get the simplest wave equation we learned as an undergraduate, the hyperbolic one, right? But this regime is not that, I mean, we already understand. I wasn't going to say it's not that interesting. No, it's interesting, but we already understand. So let's try to understand what's happening with systems like this one, which are quite more complicated, and to understand what happens with this system here, right? Well, if it's something new to us, we have to start understanding it by parts, right? By step. So the first step is make it linear. Keep this guy, which you guys are not supposed to know what a dispersive system is, and let's do a Fourier analysis of this system. That's basically our goal in just a few minutes. Okay? First, I want to mention a few things about this. Okay. So, remember that I mentioned to you that we were going to learn, right? We want to deduce famous systems from the mother equations, right? The potential theory. So we already deduced the Boussinesq system, which is a famous system, very interesting in many ways. Now let me indicate to you, I will not give you all the details, you know, it's a good exercise, let me indicate to you how to deduce the KdV equation from this. Okay, so this system, it's kind of intuitive, right? That this system here, the Boussinesq system, is a two-way wave equation, right? Look, it has two eigenvalues. It could be, depending on things, it could be actually, you know, two modes exactly on the same direction. Very good. Two modes in the same direction. But let's think that we're not in a supercritical situation. If we're not in a supercritical situation, it's a two-wave model, right? Not the two eigenvalues in that direction. Fine. Which we see here, and more or less here. So I'm going to ask now the following question. I'm going to ask myself, or ask you the following question. How can I, it's an interesting problem, how can I extract from this system a unidirectional equation, right? It's the same question that I can ask you too. How can I extract from this system, and maybe you never thought about this, so I'm going to propose indicators. How can I extract from this system a unidirectional equation? That's not so difficult, right? Because the wave equation, as we learned, is the same thing as having eta t minus eta x equal to 0 and eta t plus eta x equal to 0. Okay? So this, let me maybe put this. You can actually write this equation a little bit in this form. So it has a little bit of a two components, right? And when we do the D'Alembert solution, we actually see that we have two components. And remember, at f plus xt, f of x minus ct, right? So we have the two modes and so on. Okay. So the first thing is, so the question is, how, and I'm not going to do all the details on purpose, how to extract a unidirectional PDE from Boussinesq. And namely, this question is the same as how to get the KdV, which is the Korteweg de Vries equation. Okay, how to deduce it, right? How to get, or how to get, maybe a more proper mathematical way is how to deduce the KdV, the famous Korteweg de Vries equation that right? Russell chased the solitary wave, the soliton, and then Korteweg, De Vries later on found a way along the lines of Boussinesq, right? Not from the Boussinesq equation, but averaging, throwing terms out. They got the famous Korteweg, De Vries equation, which became reference PDEs, in particular in dispersive PDEs. Has geometrical, has many deep, important, it's an integrable system. I'll mention a little bit about this. So it's a super famous equation. How do we get that? Okay. So let's see how we do this. So go back in our presentation, or the notes, to the Boussinesq type system, which, let me write it here again. So, look, we went back to last class where we had this system where I'm not yet truncating what I call my garbage term, right? The truncation term I'm going to throw out. This is basically a shorthand notation for all the tail, the infinitely many terms from the power series. No big deal, just keep things simple. Okay, when we do our truncation, we make this 0, and we get a Boussinesq type system. This Boussinesq type system is prior to the one I just did, because recall that U tilde was speed at bottom, was not right, or actually was equal to df dx, was not the depth averaged one, right? That's not so important. I mean, we went back to this system, okay? Now, the question is, how do I specialize this system for waves going only in one direction, for a solution that only goes to the right? There's nothing happening on the left, which is a question I'll ask you also for the linear system. Is basically, if I had, let me ask this question. So let's use, to organize our mind, let's use the linear hyperbolic case first, because it helps us organize our minds. Okay, this system has characteristics like this, plus or minus 1, okay? And then I ask you the question, which I will not give you the answer, right? It's a good exercise, which is, how do I set the system, right? For example, let me ask it in a better way. So this has initial conditions okay? So how do I choose? These initial conditions so that I only have right-going information, right-going wave. In other words, is how do I choose initial conditions so I only activate the sort of plus characteristics? Right? You don't have to answer it now. It's a good, not very difficult, it's a good exercise. So how do I choose this so I can only activate these right-going exercises? I will give you the answer. Okay, I will give you the answer because it's important for the class. But you think about it. It's a fun thing. So the answer, so choose, so activate characteristics plus if ux0 is equal to eta x0. Okay? Well, yeah, here it's u tilde. Okay? Which then basically says that effectively we have this, right? Actually, plus. Yeah. Okay. So it's like if I use this data, it's almost like this system is two systems like this, because if u is going to be equal to eta, eta also satisfies this. There's like a redundancy, right? I mean, these characteristics here, let me put it again, are not activated. They're like, the equations provide that sort of channel of information that's we haven't switched on. Who cares? I mean, that's not a problem, right? The PDE is good, is nice to us. That gives us right and left modes. But I can activate only the right modes, right? And the other one stays quiet. No dynamics there. Why not? Right? So this details. But that then gives us a hint of how to get the KdV from this system. Okay? So here's the ansatz. For getting the KdV is that, okay, I'm going to say that u is equal to eta. Okay, then put it like this. Ansatz for KdV, sort of inspired by the above, right? So linear, I know that if I put u equals to eta, things only go to the right. I want to see for this guy, things only going to the right. So I say, okay. I'm also going to imitate the linear case and do u equal to eta. But that's not enough, because this guy is weakly nonlinear and weakly dispersive. And this guy was linear, non-dispersive. Right? So therefore, the ansatz, the intelligent ansatz, is to write this. And as I told you, the ansatz, I'm going to take a little drink of water, the ansatz tells your audience, when you write an ansatz, it tells your audience what you're thinking, right? So how would you read in English, or in Portuguese, Spanish, as you wish, or Chinese, how you read this ansatz? What am I trying to say to my audience when I write this? Okay. where you can consider alpha and beta small. That's the regime where we are working, right? Weakly nonlinear, weakly dispersive. So this is very nice. This is the first more serious ansatz, I think, we get. And this is cool. This is nice. Look. Now I'm going to read this in a colloquial chatting form, right? This is the ansatz. Well, let me first do, what is an ansatz? An ansatz is a form where you're trying to express how you believe the solution is going to look like. You plug it in. And you try to get something interesting and meaningful. Sometimes if you do a wrong ansatz, sometimes, not always, the math might tell you. You get an absurd thing and say, oops, bad ansatz, bad guess. Step back and fix your ansatz. But sometimes it looks okay, and the math doesn't really tell you you're doing something wrong. You might find it afterwards somehow, maybe even doing numeric computations and comparing with something you know about the solution. Anyway, right? So here, of course, this is going to work, or else I would not be wasting our time. And what does this say? This says that to leading order, here's like reading it with asymptotics terminology. To leading order, I want a right-going mode, because I know this works for the linear case, plus a weakly nonlinear correction, plus a weakly dispersive correction, because my equation is not linear and it's not non-dispersive. It's weakly nonlinear and weakly dispersive, right? Or in other words, I want my linear mode, I will allow to my linear mode a small nonlinear perturbation and a small dispersive perturbation. Okay? All right? So you plug this in. Okay, so let me say, one, this guy here is 2. I will not give you the details of the story, right? This is also a good exercise. So you plug 2 into 1. So plug 2 into 1. Then we can play with changing derivatives as before up to some order. And the goal is to write, right? Or to rewrite one as now let me help you a little more, and the goal is to find the leading order values of A and B so that system 1 can be written or can be rewritten as Okay, I'll explain the notation too. Okay, so let me come back here. So if I substitute, see, if I substitute these guys in here, I can basically rewrite these equations as two similar equations, right? So it shows that the system is redundant, right? Because, you know, one of the characteristics, not active things are propagating to the right, blah, blah, blah. So what we're going to, so the strategy here is you have to find the leading order values of A and B, leading order in terms of alpha and beta. We don't want the guys alpha squared, alpha, beta, beta squared. We don't care. They're junk. They go into the garbage can, right? So they will go, yeah, into these guys, right? So as you're playing with this ansatz, so here's the asymptotics homework, right? As you're playing with this ansatz in here, to our convenience, we can sort of change these guys, throw guys into there because it doesn't matter, play with derivatives. So for example, look, this guy is going to become this guy. So somehow the u of t will become an eta of t, right? Things will change. And then you're going to play with these guys. You're going to find conditions for the a's and b's to leading order. And at the end, you will transform this equation with this ansatz. And with these manipulations, we're going to transform this system into this one, which, just out of fun, let me ask you, do you know what hot means? Very good. Higher order terms, right? Which is the same thing as this. Just a short for that, right? These are higher order terms. And why am I putting this one here and this two here? Because these high order terms need not be the same. I don't even care. I'm not even gonna present in the calculations, I mean, in all details, I mean, how these guys look like. You don't have to worry about this. What is important is that the leading order term is the same, right? Therefore, the effective dynamics is governed by the KdV. There are many versions of the KdV, but here's our first version. So here's the famous KdV. Okay? So here's the famous KdV introduced to you, right? Doing the steps that are mentioned in words how to do, but they're not done. And look at this. This is basically a right-going linear wave with a weakly nonlinear Burger's type term, correction, plus this dispersive term, which is the XXX higher order derivative, right? Still, I hope, I have time. We'll see why this is called dispersive, okay? And if I make the dispersion 0, this is just basically like a Burger's equation, right? And we're going to at one point study a little bit this without the nonlinearity. And you see, because of this guy being a higher order term, this system here is not hyperbolic. It's some other class. This is a dispersive equation. And the dispersive PDE does its is not in the category of those second-order equations we mentioned, elliptic, parabolic, or hyperbolic. It's not. It's another class, dispersive. Right? Particularly has high-order derivative. Okay? So, good. So we arrived at the famous KdV. Now let's start doing our first, good, I have half an hour. Let's do our first exercise in Fourier analyzing these systems, and then we'll see what it means for a PD to be dispersive in the Fourier sense. Okay? Okay, so let's take our simplest system, which is this one, our hyperbolic system. And let's do what's called a dispersion analysis, right? Where we're going to get the dispersion relation, which will lead us to which is something actually we do in numerical methods also. And this is basically a Fourier analysis, as you will see. Okay? So, omega is our angular frequency, right? So this is the wave period. Let's just call it frequency. We have the wave number, which I think I already mentioned here before. Right, lambda you already know, the wavelength, right? So K is called the neighbor wave number, and this is like a spatial frequency, right? So it tells you how many wavelengths you have per 2 pi. Okay? And the dispersion relation is this. We get omega. We want to find omega as a function of k, and you'll see this why it's useful. So basically it's a relation between the two frequencies, the spatial one and the temporal one. That's the dispersion relation. That dispersion relation is basically when we can transform the PDE, that is a differential equation, into an algebraic equation. Right? For linear systems, linear constant coefficients, PDEs, we're going to do that, and that's going to make our life very, very, very easy. How? Okay? Well, let me look. Let me put it like this. Problem is linear. Constant coefficients. So using superposition, we can write the solution in the form, basically Fourier form like this. Okay, so what have I done here? I'm doing, basically, I'm using Fourier transform to represent my solutions. So basically, I'm summing over all spatial frequencies. This one is a right propagating mode. And these ones here, after the yellow plus, are left propagating modes. Is that clear for you? And these are the mode amplitudes. Right? So for example, if I have a guy propagating this way, right? This is what I mean, the mode amplitude. Okay? And look, if you're not happy looking this, you can actually put the k outside, divide by k, do this everywhere, and we have that c of k is omega of k divided by k and this is called the phase speed. Is that intuitive? Look, if this is a given k, say k equal to k1, right? This is a given phase, right? Whatever you want to call it, doesn't matter. And this guy will move to the right with this speed. Right? This guy will move to the left with that same speed. If I put here K1, 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 there are two guys, two similar guys. Right? My drawing's not perfect, but just think of two similar guys, one going to the right and one going to the left. Right? Where this amplitude of this guy here is eta 1. K1, this amplitude could be different. It's eta 2, K1. Right? And this Fourier transform representation of my solution is for the whole line. I am not considering boundary conditions. Right? It's just the whole line. I am admitting that this Fourier transform, this improper integral makes sense. So therefore, these amplitudes decay for high frequencies. Right? Is that okay? Right? And these are the amplitudes for the wave elevation. And these are the amplitudes of the Fourier modes for the velocity. Because my system is in both guys. So this is a complicated, it seems complicated, but it's not, representation of the solution of these two guys, which you can do it through characteristics, or you can do it through this Fourier representation. So I'm going to call this, right? Or usually I take one of these guys, the negative. I'm going to call this a generic Fourier mode. Okay? And if I understand what the PDE does to one of these guys, as you will see, I basically know what it does to all the other guys, because it's just a superposition of these guys with the proper amplitudes. That's how I get the dispersion relation, which is this, how omega depends on k. Let's see what happens now. Okay, but I hope I have motivated this properly. And in numerical methods, we do a similar thing for the discrete model. Sometimes trying to solve numerically a hyperbolic problem or hyperbolic system, we find out that the numerical method is dispersive. So the dispersion is numerical. It's not physical. It's not from the model. Okay. Anyway, just as a cultural comment at this point. So since the problem is linear, substitute the Fourier mode into PDE system to get save for the right-going parts, okay? Which means substitute a Fourier mode like e to the I kx minus omega t, which is just for that part. If you do it for the plus, it's going to be the same, or as you will see, you get the answer right for both, okay? So if you do this, okay, you see now a relation for the Fourier amplitudes. Okay? And what do you want to conclude? So this is basically your time frequency, your spatial frequency. You have eyes all around, right? So this basically gives us the system. So you see, this PDE, when I substitute this Fourier mode, gives me this algebraic equation, a linear system of equations, right? Right? Why did I substitute this? Because of this representation, right? That's the motivation. And because of the linearity, I can just plug in a generic guy. So what should we ask here? Is this a good system for us? Are you happy with this system? At first I would say no. Because, if I don't ask for anything, it looks like this guy are going to be zero. So that's a trivial solution where nothing is going on, nothing's happening. So therefore, what we need to do, so the important condition here is that the determinant is zero, so we get a non-trivial solution. Okay? Which implies that omega squared is equal to k squared, which gives us the dispersion relation omega equal to omega k is equal to plus or minus k. Which already, if I put it here, somehow already gave us right and left modes, right? Okay, and what is the phase speed? The phase speed plus or minus 1, as we expected, which this is a long way to get exactly what we will get here if we looked at the eigenvalues, plus or minus 1. Right? Now we got the same thing through the dispersion analysis. But then the good thing, okay, maybe let me use this board. Let me come to this board so I can save us time, is now that I know that omega over k is plus or minus 1, I know that my solution is like this. This is a Fourier representation of my solution. I forgot the k here. Right? So this is the Fourier representation of my solution. And then how do I get, to really have the final answer of the Fourier representation of my solution, what do I need to do? What do I don't know here? What still needs to be calculated? I don't know the Fourier amplitudes, right? I don't know this guy, this guy, this guy, and this guy. But I have not imposed yet the initial conditions, which is making this 0, this 0, this 0, this 0. Okay? And maybe through the initial conditions I can maybe find these guys. Okay? So this is, okay, I still have some time, perfect. So this is the representation, excuse me, this is the Fourier representation of my hyperbolic system. Okay? And now I'm in a position to define to you what is a dispersive system. Note that the hyperbolic system, the phase speed independs of the Fourier frequency or the spatial frequency. Look at here. Plus or minus 1. So a dispersive system, so if Ck is a constant, that's typical of a linear hyperbolic system. And if C, the phase speed, is indeed a function of k, that means this implies that Fourier modes travel at different speeds, then this implies that we have dispersion, or that is that we have a dispersive PD. Okay? So let's say I have 10 minutes or less. Let me prepare, then I'll do this a little slower next class, but I want to define, because today is Wednesday, I want to define what a dispersive system is, right? This class I've been talking about, said I was going to do it, and I'm almost ready to do it. So let me do it here. Something I will show you in more detail next class. So now consider the linear potential theory, first in dimensional form. With dimension, okay, dimensional form. So it's like this. So this is, if you take the potential theory in dimensional form and you linearize it, right? You throw away the terms where the alpha would appear. This is the problem you have to solve in the strip, the fixed domain. Remember, it's not really a free boundary problem. I'm considering the flat bottom case. Here's G of gravity, and double check this, that actually you can eliminate eta, right? We can to find it at, say, the end, after we solve the problem, using the linear free surface condition, which is written like this. Okay, that's very easy to check. So this is the linearized potential theory problem, the one we started the class with, which is very complicated. Okay, Neumann condition at the bottom. The free surface condition becomes simpler and can be applied at the undisturbed level. Laplace stirs Laplace, and we can actually eliminate eta, and at the end, if you solve for phi, you have the wave elevation by just computing this. It's the time derivative. So in the linear problem, the wave elevation is the time derivative of the potential at the free surface, at the undisturbed free surface, with the 1 over g gravity. That's all. Okay? Very simple. So basically, eta becomes a little bit like a passive variable. It sits there and waits for you to solve the problem, and then you know what eta is. So very simple. Okay? So let me write the dispersion relation, right? I don't have time. Also, I don't want to rush. I'm going to do a similar Fourier analysis of this, and we will find that the dispersion relation for this problem is this. So look here, compare this with this. Or even better, with this, right? Because it's squared. So in the linear hyperbolic case, omega squared was equal to k squared. Now here, omega squared is equal to this complicated function, which means that c is a function of the wave number, therefore dispersive. Right? I mean, divide this by k squared and take the square root. This is a complicated function. Now look at something quite cool now. Look at this. Take the limit of k going to 0, which is long waves. Okay? This means that omega squared k is equal to, well, if hyperbolic tangent is very small, I can approximate, let me put it this way, to kg times kh. Agree? Right? If you take the expansion, which is basically equal to gh k squared, which then implies that the phase speed is equal, or is approximately, the square root of g h0. Here should be have h0. which is the shallow water speed we saw before and tells us that tsunamis travel very fast, blah, blah, blah. Okay? So you see that the dispersion relation, there's a consistency in terms of the dispersion relation. So this is of the full problem, right? And in the long wave limit, which is the shallow water case, we recover, right? But this is the dimensional form. We recover, look, omega squared is equal to k squared. And here's the speed squared. Here it was normalized to plus or minus 1. Okay? So in next class, next week, I will come back to this problem. Right? I just wanted to get things prepared. So we have to see how we come from here to here. I did not show this. Right? You should check on your own that this is the correct linear problem and that actually you can remove the eta for the time being from the problem. That's convenient. It's no big deal. Right? And then we're going to do the Fourier analysis of this guy. That's going to be my first exercise on Monday, to do the Fourier analysis of this guy. In a similar way we did it here, but it's more difficult. It's like not a big deal. But anyway, let me not say anything now because it's going to go through your heads because, right, I haven't showed it to you. So I'll make more comments on Monday. But that's our starting goal on Monday. Okay, so that's very good.